Hello, and welcome to this CodeRage session on connecting to the Internet of Things. My name is Brian Alexakis, and I work at Embarcadero Technologies as a product marketing manager. Lately, I have been blogging a lot about the Internet of Things and how it is transforming the way we as human beings are connecting to technology in new and exciting ways. Over the next half hour, we'll be discussing what the Internet of Things is, what kinds of new experiences IoT brings to your connected apps, and the important aspects to consider for future application development. We will get into some examples of how to connect your applications to the Internet of Things. Demos will include a deployed app used to remote control video playback on another device, Bluetooth app tethering with a wearable health device which monitors heart rate from Zephyr, and using a REST API over Wi-Fi to pilot a Parrot AR drone, and finally integrating an SDK provided by Thalmic Labs to capture input data from their Mio gesture control armband. There is a lot of buzz associated with the term Internet of Things as an emerging technology. But what exactly does the Internet of Things mean? What are things? What does the Internet have to do with it? As you can see from a few selections of gadgets, wearables, and devices that can be considered a part of the Internet of Things ecosystem, there's a very broad range of solutions, some of which connect to applications on your phone via Wi-Fi, for example, home automation applications which interact with smart light switches, air conditioning, heaters, and etc. Wearables like smartwatches or mobile health devices, which either provide information in the form of notifications or gather information from you in a multitude of ways. This input can take the form of touch, gesture, voice, various forms of biometric readings, and even thought itself. Applications span over home automation, industrial, medical, security, virtual reality, gaming, and other forms of entertainment. The commonality here is the ways in which these gadgets and devices interact with information and the connected app. That is to say, things are capable of being interconnected with one another. This interconnectedness provides developers a true opportunity to deliver new experiences and solutions to the end user. So why all the buzz about these things? I think the main reason is that many recognize that IoT devices are really changing the way that end users experience and interact with their devices. Gadgets and wearables like watches provide new user experience elements. So the Mio gesture control armband from Thalmic Labs, for example, is a haptic sensor that uses the body itself as a form of input. Consider the expanded user experience that a smartwatch creates when connected to a phone. When I'm out for a run, the last thing I want to do is fish my phone out of my pocket, unlock and swipe down, read the notification or the alert, and then engage with the device if needed. All the while, I am taken out of stride, and these alerts can happen often and become a big distraction. So, using a smartwatch, I can glance down at my wrist, consume the alert, and decide if any further action needs to be taken. But 9 times out of 10, I don't really need to respond at that very moment, and it just isn't that urgent or important. So the watch has had a rather profound impact on me personally in regards to how I consume my notifications. By not having to engage my phone and disengage from what I'm currently doing, I can stay focused on the task at hand, whether that is being out for a run or if I'm working on a project. So when you as a developer are considering how to build Internet of Things solutions into your connected app, it is important to keep in mind that it's more than just connecting to these gadgets and devices, but it's about gathering information, sharing information, and presenting information in new and interesting ways. When it comes to gathering information, new forms of input are placing the human body itself front and center within the Internet of Things ecosystem. Consider what it means when your user can suddenly control your connected app by waving their hands around in free space, or by thinking a thought, or by flexing their hand in one way or another. There are new types of connectedness or topology around data flow, one in which the mobile device presents a central area that connects to these devices, gadgets, and wearables, that connects to the cloud, like social network services or the company backend enterprise data, for example. So apps are no longer standalone, they are distributed between gadgets, devices, and wearables and the cloud. So let's take a moment and actually define the Internet of Things and some terms that go along with it. First of all, what is a thing? Well, things are sensors, sources of input, controls, gadgets, devices, wearables, and pretty much everything else that connects and interacts with applications. Things typically serve a specific purpose and can radically change the user experience with applications with which they connect. So what does the internet have to do with these things? Well, these things collect data, lots and lots of data. And this data is received by a connected app, which can be stored in the cloud and other data store endpoints. The internet empowers the data to flow seamlessly from one device or gadget to the connected app and be consumable by the end user at any time and any place. This effectively extends an app user experience to include anything or a combination of things whereby by themselves they wouldn't necessarily have that internet connection or data availability. So there are different kinds of things. Let's start with a device. Devices are programmable, which means a program, your code, can run directly on the device itself. In order to facilitate this, the device will have an operating system. It could be Linux, Android, Windows, even iOS. In order to access the features of the device, programmers can use the Software Development Kit, or SDK, provided by the developers of the device. Altogether, the device and the operating system on which it runs is referred to as a platform. Gadgets are also a kind of thing. Gadgets are sources of information that range from any kind of sensor data to gesture commands, proximity data from beacons, and traditional forms like mouse input. Gadgets do not run custom apps on the device itself, and in that way can be thought of as a read-only device. Some examples of gadgets include the Leap Motion, Thalmic Labs Mio gesture armband, and the Zephyr heart rate monitor. Typically, data is read in by a connected app via the gadget's application programming interface, or API, which is provided by the developer of the gadget. A standardized Bluetooth profile like GATT, or a REST interface provided by the gadget's optional web server. Hardware innovations are continuing to dissolve the boundaries between human and machine. Our bodies are being placed front and center as a new form of input within the Internet of Things, and emerging haptic technologies have applications that stretch across contextual wearable computer devices, human-computer interactions, or HCI, entertainment, video games, virtual reality, industrial, military, and the list goes on and on. Really, for the first time in the history of human experience, we are able to engage with technology in ways that have been the mainstays of science fiction. Take telekinesis, for example, defined as an alleged psychic ability which allows a person to influence a physical system without physical interaction. Well, devices like the emotive epoch, which literally reads your thoughts via an EEG, are actually enabling solutions driven by just thought as the sole input. And when you connect that to the Internet of Things, telekinetic powers are not alleged anymore, but actually a reality. Consider a disabled person, for example, that now can reach out and interact with their surroundings through home automation driven by Internet of Things solutions. And I would challenge you to consider your connected app and whether it can live up to Arthur C. Clarke's famous quote, "Sufficiently advanced technology is indistinguishable from magic." Designing these new experiences that are part of the Internet of Things will become the next logical step following traditional multi-device based UX and UI design. What kind of new design restrictions need to be considered when dealing with gesture-based input? What does it mean when your users can suddenly control your connected app by waving their hands around in free space or simply by thinking? Biometric data whose timely notification could really be the difference between life and death. We are going to cover the four types of Internet of Things connections. Consider the many devices we saw earlier in the presentation. There are literally hundreds, if not thousands, of devices in the ecosystem today. They all have different varying levels of complexity. They all pretty much have a CPU and some kind of memory, but they may not have full-fledged operating systems. They may not have a Wi-Fi radio, for example. Maybe they do have a full-fledged operating system that can take a loadable packaged app. Let's consider the Android-based Internet of Things device, Google Glass. Google Glass can take a loadable packaged app and serves as both a device that can read in data from the user and feed it data back to the user. In this way, Google Glass is considered a device and a gadget at the same time. We will look at Bluetooth and Wi-Fi communication via app tethering by examining a mobile app which will control media playback on the desktop. Next, Bluetooth LE or low energy, also called Bluetooth smart devices. They're very low powered devices that generally do one thing and do that one thing well. Bluetooth LE devices are very effective in mobile medical application, for example, as a wearable heart rate monitor. They are very low-powered devices that can run for long periods of time, that passively read biometric data, other kinds of data, and transmit it over a gap profile. So we're going to examine this with the Zephyr heart rate monitor. Another way to connect to the Internet of Things is through REST APIs over Wi-Fi. Smart home solutions like lights, thermostat, and door locks tend to use the home's Wi-Fi network to transmit its REST API. Other devices have Wi-Fi routers built right into them and pair directly with a Wi-Fi enabled device. We will be exploring how this works with the Parrot AR Drone 2.0. Lastly, devices that have specific platform SDKs can be linked into your application and be used for solutions that are programmed against that SDK's API. We'll be looking at the Mio gesture control armband from Thalmic Labs. Okay, the first step to getting this thing going is to go ahead and navigate to the bin folder from the Mio SDK. Grab the Mio 64 DLL from the bin folder and put that into your project deploy debug folder. You pop up a command prompt and navigate to your project debug folder and execute the mkexp command by entering mio64.a and mio64.dll. This will go ahead and create the .a file. As you can see, it was just created here. And we're going to go ahead and add that to our project. So go back to your project and right-click and add. Navigate to your 64 debug folder. And we don't see it here because currently we're looking at all CPP files, so we change that to all files. Select the .a file and hit open. We've now included it into our project so that we can link against it. Copy in the SDK source code. I've navigated back here to my Mio SDK download directory, and I'm going to go ahead and go into the include, and I'm just going to go into Mio, and I want all these files here. So I'm just going to grab the Mio folder, copy, go back to my project, and I'm just going to paste it in here. And then I'm going to come back here, and similarly to the .a file, I'm going to go ahead and right-click on our project and go to Add. Open up the file and just copy everything in here. And you'll see here that we've got the two files that we really need, the .hpp and the libmyo.h. Let's add some components. First of all, add a memo. This will be used to trace out the gesture control data that gets received by the myo. Next, add a rectangle. This rectangle will be used to visualize the input that gets received by the myo. And lastly, add a timer. This timer will be used to poll the myo device at regular intervals. We're going to go ahead and change this down from 1 second to 10 milliseconds. So now that the components have been added, let's go ahead and examine the code under the hood. I've already incorporated the demo sample code from the SDK, and starting from the includes, we just have some standard includes here, and here we are actually including the myo SDK itself. There is a data collector class that basically serves as the interface between the connected app and the myo device itself. There are some properties here that are tracking its positional data, the roll, pitch, and yaw, as well as its current pose. And the onArm is referring to whether or not the device is actually being worn. The onUnpair function gets called when the myo gets disconnected or unpaired by the user. OnOrientation update will get triggered when the device is orientated. This gives the original positional data for the myo as a point of reference. OnPose automatically gets called when the myo detects that your fist is making one of 5 recognizable gestures. Those gestures are a clenched fist, a spread finger fist, a fist where your hand is projected to the left, and another where your hand is projected to the right. And it can also detect the thumb being pressed against the pinky. And lastly, it recognizes when your hand is doing none of those poses and is considered at rest. OnArm recognized is fired when the myo armband is detected as being worn on the arm. And OnArm lost, as the name indicates, triggers when somebody takes the myo off of their arm. Okay, lastly we have this print statement here. Now I've changed the print statement from its original purpose to interact with that rectangle that we added to the stage. So the first thing that happens is we go ahead and clear the existing memo line, and then we check if the myo is on the arm. And if it is, we want to let the program know whether it's on the left or the right arm. So it just gets spit out to the memo. After that, we're going to go ahead and capture the pose, if there is any, by simply assigning a string here and then tracing that out as well to the memo line. And then we're going to analyze what pose. For the purposes of this demo, I'm just looking at whether there's a fist or not. If there is a fist, then we take the scale of the rectangle and double it on the X and Y. Otherwise, we just return it to normal. Lastly, we can just print out some more positional data, the raw, pitch, and yaw, and apply that positional data to the rectangle. These numbers are just kind of magic numbers that I played around with that worked well with the orientation, and you may want to change these values around for your own purposes. Lastly, we have some variables within the class that track whether the arm is on, or rather if the myo is on your arm, which arm it's on, the positional data, and the current pose. Moving on from the class, we have the global data collector class and the hub. The myo hub is basically the sort of command center that the myo armband connects to. The myo hub is part of the SDK, and when we begin the application at our point of entry under the T-form here, we actually initialize the hub by adding the collector to the add list, by passing the collector in rather to the add listener method here, and then after that's added, we just simply begin the timer, and this timer will get run at whatever interval we set, And when that interval fires, it pulls the device by telling the hub to run and collecting its data. And so putting this all together, we actually are able to see the Mio in action. So let's go ahead and see what that looks like. So here you can see the rectangle translating as I move my arm to the left and to the right, and up and down. And here we see the fist doubling the scale, and also the rotational value is being interpreted. Okay, let's next examine the Parrot AR Drone 2.0 and how we are able to issue commands to it from our connected app using REST over Wi-Fi. The Parrot AR drone itself has a router built into it. This router will pair with any device capable of communicating over Wi-Fi. So it could be your smartphone, whether it's Android, iOS. This could be your laptop or a tablet. So App method includes a component called the UDP client. This makes it extremely easy for our connected app to communicate over UDP. Here we've inputted the IP address of the drone as well as the port. The next component to look at is the timer. The timer is used to create an interval of 100 milliseconds. Every 100 milliseconds, it will issue a new command to the drone, and those commands are going to basically correlate to the various buttons that I've added to the form, from landing to takeoff to spinning left and right to going forward and in reverse and strafing left and strafing right. So let's go ahead and examine the code that is driving this connected application by first examining the timer. Here we begin by asking if the drone is currently flying or is landing. If it's not flying, we don't want to issue commands to it. And if it's in the process of landing, we certainly don't want to interrupt that. So in either of those cases, we're going to cancel out of here. And then basically we have a variable that's tracking the current direction that is bound to a key press. And depending upon what button or key press is currently engaged, it will issue the correlating command here with this giant switch statement. So when it comes time to actually issue a command to the drone, this send command function gets invoked, and the command is read in as an ANSI string. The first thing that happens is we check to see if the UDP has an active connection. If not, we go ahead and make that connection. And of course, this will use the properties set in the object inspector that I pointed out earlier. Here we have a format command that basically is going to take the string passed in and massage it into a format that the drone can actually use. If you'd like more information on the technical bits behind this part of the code, refer to the end of my slide notes where I link to a couple of blog posts that'll give you more detail. Once that formatted string is ready, it's just simply passed into the UDP send command and off the command goes. So let's take a look at the What a Simple Drone Control app in action from the Android view itself. So I just hit the takeoff button, and here you can see that as I push the buttons, the drone is issued the command and flies as you would expect. Next, we'll take a look at the WASD control app from the Bluetooth keyboard paired on Android. So here I've got the phone in my pocket, and the Bluetooth keyboard is paired to it, and I can use the WASD. Oh, I just bounced off the wall there, but of course I can recover from that and continue flying. So this is using the WASD buttons, and anybody familiar with gaming will recognize what that is. And I must say, it actually provides a quite high fidelity of control. It's a lot of fun. Thank you for taking the time to watch my presentation on the Internet of Things. We discuss the 4 ways of connecting your app to the device and gadgets of the Internet of Things ecosystem, and further considered how the human-computer interface is being bridged by the devices and gadgets of IoT to extend the functionality of your connected app with new user experiences. These new kinds of user experiences demand new solutions and design approaches to UX and UI as a new paradigm following mobile, multi-device applications. Please check out my blog posts for more details covering the demos I presented.
Marcus actually apparently has commented, well, this is his field of expertise apparently, and he commented that you probably do not want to use a $20 TDCS device to run current through your brain. So that's probably good advice. Remember, you only have one brain, you can't replace it. So definitely put some research into this and make some considerations before running current through your brain. But either way, it's interesting to learn about this and interesting to see that this is something people are doing at home. And I think we'll definitely be seeing more of this in the near future as a recreational pastime, if you will. It was interesting. The first time I did this presentation, TDCS wasn't any sort of it was totally a clinical process. But then in that time, I was refreshing my slides at one point and discovered, oh, now people are doing this at home. It's a hobby. So very, very interesting that's happened. All right, so a few more questions will come in here. Other than tinkering entertainment, what are the likely applications of this technology, especially in light of the hype cycle that I showed? What's happening in the real world with regard to this technology? So there's a few devices. I showed you the link. There are a few devices coming out there. This is it's just now entering the consumer space, really. The NeuroSky was really early on. Like I said, just one electrode. It really just tells you, concentration was the only thing it could really give you feedback on. But then the Muse and the Emotive Epic have really expanded what is possible with this technology. And so we're just now starting to see it. A big place I've seen a lot of work with it is working with people that are disabled, that don't have the ability to move their arms and legs, like the guys in the music video I mentioned, and also the work in gaming. That seems to be the two big applications. In gaming, frankly, oftentimes does push the envelope for technology. So it's interesting that I think that's one of the reasons that they're targeting that area is because people tend to adopt things quickly there. But I think also the being used for research purposes, as far as especially what's the market research? So having somebody view a movie trailer or a pilot for a TV show and get some feedback as far as their attention and focus and stuff like that from their brain. And Marcus pointed out that's not incredibly accurate, but you can use this in combination with surveys and other mechanisms that you can use to collect feedback, and it just adds another input point in your data collection. It would be interesting research project to read sound from a brain powered by a cochlear implant and see if those signals match. That would be interesting, actually, to see if that the implant from the would match up. Because interesting. Yeah, that's an interesting idea. Numentia is a company with open source SDK that models human cognition learning. It might be interesting combining with the brain sensing devices with the software. Okay, that's great, Mark. Thank you. About the drone, I think Parrot only has movement controls. Are there any other drones that also allow you to control its payload, such as camera, video feed, etc.? So the drone allows you to send movement controls, and then also you can read the video, although I haven't had any luck decoding the video yet. It's video encoding is not my strength necessarily, and so I haven't figured out completely how to read the video. I have not found any other drones that do have an API that I can work with, or at least not in the affordable price range. That's one thing I asked about the Parrot. I think it's like $300, so it's a very affordable drone comparatively, especially considering 5 years ago they were only used by the military and very expensive. But I do have another demo. When I don't have the drone with me, I can use a little Bluetooth controlled car, and the Bluetooth car, because it's Bluetooth, able to interact with the Bluetooth and control it that way. And I believe Daniel TT actually put that the interface for talking to the Bluetooth car together, and then all I did is added app tethering so that I could control it via the main app. So if you notice, the screenshot of the app had a slider that said drone, another slider that said Mini Cooper, and the Mini Cooper would be the Bluetooth car. And it had much more limited left, right, forward, backward, no up and down like you have with the drone.
So the drone has Android inside of it, but other than hacking in, you don't send apps to it, but it has the APIs for sending commands and getting data from the drone. And we're going to continue to support more and more of these Internet of Things devices with standard components and RTL support in the future. So stay tuned there to our blogs as we do samples and examples. And Jim has a component, has some components for some of the other devices he's playing with. So his Delphi.org blog is a good place to keep track of the research that Jim McKeith is doing in this Internet of Things and devices. And then Brian's doing weekly blogs on his blog on different Internet of Things devices. So stay tuned on a weekly basis for a new device each week on this connected Internet of Things world. Georgie's asking, UDP is sometimes not reliable. What if a packet is lost control of the drone? Do you repeat it? Okay, so there's in the AT commands, there's sort of a sequence number that's part of each command and the data handshaking so that you can see which commands were sent and which were executed, and you can look for an out of sequence or a lost sequence response coming back. So you can look at the API. Again, you join the Parrot AR drone developer program, and they give you access to the documentation and the API. So there's that part for doing it. And again, UDP is how they've decided for this version of the drone. There's other drones that use radio frequency to command because they can get farther reach, thousands of feet with higher performance radios for some of these bigger drones. Again, this is $300 drone, and so it is an access point itself, and that's how you connect to it. And they've made the decision to use UDP for the commands, and then they have other ports for the video, and I've got a plug-in for my drone, which is a data recorder and also a GPS, so it plugs in and you can get the location of where your drone is, and you can also pre-program patterns of flight, selecting points on a downloaded map from Google Maps, for example. You tap points and it gives you the coordinates, the GPS coordinates for those. And you can say, take off from here, where you are right now, go up to 10 meters, fly to this next point, go up 30 meters, fly to another waypoint in GPS, and then maybe go down to 10 meters, and then and so on, to have a pre-programmed flight mode. And that's using this plug-in add-on for the drone. I forget how much it costs. It wasn't that much. And it also does flight data recording of how the drone flies and its high altitude locations. So you can pre-program flights. I used it at home until I crashed it into a tree to fly the pattern of my roofline gutters, so I could use the downward-facing camera to see if my gutters were clogged with leaves before I got on the ladder to go up. I just downloaded a Google map of my house and clicked on the points along the outline of my roofline, and then I told it to fly, and I just sat there on my iPad with an app looking at the downward-facing camera. So again, there's a sequence number. I forget what they call it. I'd have to go back and look. But you can join the Parrot AR drone developer program and download the APIs and see how that's handled, Georgie. So, yeah, packets can get lost. Absolutely.